Okay, good morning, children. So today we are going with science, that is physics, magnetic effects of electric current. So the main thing what you have to observe is what are the magnetic effects or electric current or magnetic effects of electric current. So in the physics chapter, so we are dealing with the physics one. So let us see what are the magnetic effects of electric current here. He has given in detail here in this chapter. So if you have the textbook, go to the textbook once again, or you can go with the study material what I sent with you. So you'll get the answers for everything there. So I will be doing with this one. So I told you in the last class also what are the effects of effects of electric current. So I told you how electricity is produced also, what are the uses of electricity and what are the uses of magnet also, and I give some examples on magnetic effect of electric current and everything also. Let us see what are the effects of magnetic electric current according to the subject wise now. So what he's saying is here so in electricity we learnt about the heating effects of electric current. What could be the other effects of electric current? We know that electric current carrying wire behaves like a magnet. Let us perform the following activity, reinforce it. So what he's saying is, so any conductor in the sense any wire which is carrying an electric current, it behaves like a magnet. So why it behaves like a magnet? That is a question here. I told you already in the last classes also why it behaves like a magnet. So if a conductor or a good conductor, if it is carrying electricity, good conductor in the sense carrying electricity, so when the electricity is passing in the conductor, so it behaves like a magnet. So why it behaves like a magnet? What are the factors behind that and why it is going like this also? So we shall study in detail about these things, and he has given one examples also. I told many examples in the last classes also how it behaves like a magnet carrying electricity. I told you give the example of the wire. Take one wire which we have in your home. If you want to conduct it practically, but don't keep it in mind that use the battery cells in the cells. I told you 1.5 volts or 2 volts or 3 volts, whatever it is. You connect it to a copper wire or whatever the wire which you have in your home, connect it to the batteries or what we call cells. Then the electricity starts flowing in the conductor. When electricity starts flowing in the conductor, then it starts behaving like a magnet. When you bring some iron fillings means which contains some sort of irons, when you bring near to it, so the wire starts attracting the iron fillings here. So why it starts attracting the iron fillings? It indicates that each magnet starts behaving like a magnet. Means in the sense each wire, when electricity is passed in it, it starts behaving like a magnet. So if you go for that, magnetic field and magnetic field lines he has given there. So what are magnetic field and magnetic field lines here given? So if you take a bar magnet, what do you mean by bar magnet? Bar magnet in the sense a magnet which is in the form of bar. So this is a magnet. Imagine this is a magnet. It behaves like it is a bar magnet. So it has two poles. One is north pole, one is south. So we have two types, one is north and one is south. So here a compass needle gets deflected when brought near a bar magnet. A compass needle is in fact a small bar magnet. The ends of the compass needle points approximately towards north and south directions. The ends pointing towards north is called north pole. If I take a compass in the sense which gives the direction of direction of anything. It is a east or west or north or south. When you bring the compass near the magnet, bar magnet, it reflects in the form of north and south pole. The end pointing towards north pole is called north pole. The other end that points towards south is called south pole. Through various activities, we have observed that like poles repel while unlike poles of magnet attract each other. Means like poles repels. Repels means when you bring north and north, if you take north and north together each other, they start repelling. Repelling means they will not attract each other. North and north. If you bring north and north here, so when you bring north pole to north pole, so when you bring very near each other, it starts moving away from this side. Why it starts moving away in this? Because like poles always repulse each other and unlike poles attract each other. Means north and south attracts each other, whereas north and north or south and south, they will repel each other. Is given here. The iron fillings arrange themselves in a pattern as shown in the figure. Why do the iron fillings arrange in such pattern? Why does this pattern demonstrate? The magnet exerts its influence in the region surrounding it. Therefore, the iron fillings experience a force. The force thus exerted makes the iron fillings to arrange in a pattern. The region surrounding a magnet in which the force of the magnet can be detected align themselves represent the magnetic field of range. So when you bring the iron fillings, so iron fillings generally it might be observed what we mean by iron fillings. So if you don't have iron fillings, you do one thing. You take a magnet, bar magnet or anything magnet, you take that magnet and keep it in the dust. Dust in the sense, manali mannu ಏನಾದರೂ ಅಂತದ್ದು ಇದ್ದರೆ ಅದರಲ್ಲಿ ಹೋಗಿ ಆ ಮ್ಯಾಗ್ನೆಟನ್ನು ಜಸ್ಟ್ ಯು ಶುಡ್ ರಬ್ ಇಟ್. ರಬ್ ಮಾಡಿರೋದ್ರಲ್ಲ ಅಲ್ಲಾಡ್ಸೋಕ್ಷಣ ಏನಾಗುತ್ತೆ ಅಂತಂದರೆ ಫಾರ್ ದ 2 to 3 minutes you can observe that the magnetic small types of iron things which are present in that soil, they will be attracted to the magnet each other. So they will be attracted completely to each other, so that those attracted things we call it as iron fillings. So when you bring these iron fillings very near to the bar magnet, they will form a pattern. Which type of pattern is given? It is given in the figure 13.2 there. They behave in this pattern. In this pattern, in the sense, magnetic field is a quantity that has both direction and magnitude. If you have the textbook, just to underline this very point, it is a very important one. Magnetic field is as both quantity and as both direction and also magnitude. Direction of the magnetic field is taken from the direction which has north pole of the compass moves inside it. Therefore, it is taken by convention that the field lines emerge from north pole and emerge at the south pole. Underline this one. They start from the north pole. Where they start? The iron fillings, they start from the north pole and end in the south pole. This is a very important thing here. Why? Because if you take any magnet, especially dealing with the bar magnet here, when you take the bar magnet, what happens here it is, so when you arrange the iron filling, when you drop the iron fillings here, you can observe that the iron filling starts from the north pole and they will be ending in the south pole. So they start with the north pole and end with the south pole. This is a very important property of a magnet. What is the important property of a magnet is, they start in the north pole but end in the south pole. It is given in the figure also. So you can find a closure in the sense it will be always in a closed form. There it is. The relative strength of the magnetic field is shown by the degree of the closeness of the field lines. The field is stronger, that is the force acting on the pole of another magnetic place is greater where the field lines are crowded. No two field lines are found to cross each other. Very important one. So when you see the lines here, from when they are emerging, I told you already, from north pole to south pole they will be going. They will be going from north pole to south pole. So when they are going from north pole to south pole, you can observe that they will not cross each other. That is very important one. Not cross each other in the sense they will not come or they will not go in each other. No two fields are found to cross each other. If they did, it would mean that the point of intersection, the compass needle, would point towards the two directions, which is not possible. That is what we are saying. So if they pass each other, the compass should show both directions. So the compass cannot show both directions. Why? Because it shows only in one direction, which is whether it is a north or south or east or west. If it is pointing to north, it shows to the south. If it is pointing to east, it shows to the west. So what we observe here, it is the both poles are pointing here. So the iron fillings or the magnetic field start from north pole and end in the south pole. This is the property of the magnet. I will tell you what do you exactly mean by this. Is the definition, not definition. This is just a fresh up points for you so that you can understand what are the properties of magnets also. Or you can suspend a bar magnet, take a thread and tie the thread to the bar magnet and suspend it in the air. When you start rotating it, after some times it comes to rest. Rest means it stops there. When it stops there, it always shows the direction of north and south only. Anywhere in the world, when you suspend a bar magnet or any magnet, it always shows two directions. It is north pole as well as to the south pole. This is one of the property of the magnet. Magnetic field due to current carrying conductor. This is very important one. So what happens if the magnetic field carrying a electric current? He has given one activity, but don't write to this activity because for this we need this activity can be done in the school only. So just to go through the activity here. So what determines the pattern of the magnetic field generated by current through a conductor? Does the pattern depend on the shape of the conductor? We shall investigate with an activity. We shall first consider the pattern of the magnetic field around a straight conductor carrying current. So what he is telling is here he has taken different types of magnets and he is showing us how the magnetic field is there. For example, if it is a bar magnet, it is from north pole to south pole. So, or if it is in a form of a cardboard, or it is in a form of a circle, or it is in a form of a cube, or it is in a form of any shape. So, how the magnetic fields will be there. So, the deflection here is given there. I told you already, it is from north to south. What happens to the deflection of the compass needle placed at a given point if the current in the copper wire is charged? To see this vary the current in the wire, we find the deflection in the needle also changes. And one thing is, when you change the direction of the field, it means, I told you already, when you are doing this experiment, take only the battery cells, don't use directly it in your home, that is 240 volts, it will be there, it is very dangerous. So don't conduct these type of experiments in your home. It is better to take battery cells, either 2 cells or 3 cells, connect it to a wire and you can see that. If you change the terminals of the wires in the sense positive to negative, negative to the positive, when it is connected to the compass needle which shows the directions of the magnetic field. So if you change the field there, field in the sense if you change the compass there, in the sense if you change positive, negative, positive, the deflection will be totally changed here. From positive to negative, the deflection will be in the positive direction, and if you change to negative, positive, the deflection will be in the negative direction there. He has given there. He has given right hand thumb rule here. A convenient way of finding the direction of magnetic field associated with the current carrying conductor is given in figure 13.7 is saying. So he is given thumb rule here. You can see, you can observe there. Very important one. This question may come in the exam because many times is asked what is Generally it is Fleming's right hand thumb rule, but it is not mentioned the word right hand thumb rule. Just he has told right hand thumb rule, but it's Fleming's right hand thumb rule. What is it? Imagine that you are holding a current carrying a straight conductor in your right hand such that the thumb point towards the direction of the current. If you are holding like this, if you're holding like example he has shown in the figure, if you're holding like this the conductor, what is the thumb shows here, it is the right hand such that the thumb points towards the direction of the currents. So the direction of the current is flowing from here, and then your fingers will wrap around the conductor in the direction of the field lines of the magnetic field as shown in the figure 13.7. This is known as right hand thumb rule. Simple, it is very thing. So when you hold a conductor, when you hold the conductor in this way, so if the current is flowing in this direction from this to here, the thumb represents the flow of the current, and the fingers which you are holding it, which are wrapping the conductor, they show how the magnetic field is moving around the conductor. This is first rule there. Magnetic field due to current through a circular loop. I told you already what happens if there is a conductor in which you can see how many types of instruments are there where the current is flowing through them. In that he has given one thing, that is magnetic field lines, the field produced by current carrying a circular loop. Circular loop in the sense it is in the form of a circle which is in a circular loop. How the magnetic field is there? He has given clear picture in the textbook there. We have so far observed the pattern of the magnetic field lines produced around a current carrying the straight wire. Suppose this straight wire is bent in the form of a circular loop and the current is passed through it. How would the magnetic field lines look like? We know that the magnetic field produced by a current carrying straight wire depends inversely on the distance from it. Underline the word inversely. I told you what you mean by proportionally. You get these words in maths: direct proportional, indirect proportionally. Here we are getting the word inversely. Inversely means deadly opposite. If it is not straight, inversely means it will be down there. Larger and larger as we move away from the wire. By the time we reach at the center of the circular loop, the arcs of the big circles would appear as straight lines. Every point on the wire carrying current would give rise to the magnetic field, appearing as straight lines at the center of the loop. By applying the right hand rule, it is easy to check that every section of the wire contributes to the magnetic field lines in the same direction within the loop. And also given this rule is also called Maxwell's corkscrew rule. So you can see the figure there. So if you see the top and bottom of the conductor there, they will be round, and when they start coming down, they start moving down, and they change the direction when they are in a straight line. When they are in a straight line, they change the direction there, and again if they come down, again that it will be totally reversed there. Reverse in the sense when it is upside in the top and center, it will be straight, and down it will be totally opposite to the first side. First side in the sense downside, down of what the down we are seeing in the figure there. And also he has given magnetic field to a current in a solenoid. Solenoid means a coil of many circular turns of insulated copper wire wrapped closely in the shape of a cylinder is called solenoid. Underline this one also if you have a textbook. While going through it, you may get the question, what is solenoid? A coil of many circular turns, insulated copper wire wrapped closely in the shape of a cylinder. If you take a copper wire, go on winding roundly, then it is called a solenoid. So how the magnetic field will be there when you pass the current through the solenoid? ನೀವು solenoid ಅಂತಂದರೆ ಆ ಕಾಪರ್ ವೈರಲ್ಲಿ ಪಾಸ್ ಮಾಡಿದಾಗ ಸೊ ಅದರಲ್ಲಿ ಹೇಗಿರುತ್ತೆ, ಮ್ಯಾಗ್ನೆಟಿಕ್ ಫೀಲ್ಡ್ ಯಾವ ಪೊಸಿಷನಲ್ಲಿರುತ್ತೆ ಅನ್ನೋದು he has given there. One end of the solenoid behaves as a magnetic north pole while the other behaves as the south pole. This is very important one. You should underline it. One end behaves like a north pole and another end behaves like a south pole. The field lines inside the solenoid are in the form of parallel straight lines. They are not either in the last we saw either they are bent upside or downside. Here it is in the form of straight line. This indicates that magnetic field is the same at all points inside the solenoid. That is, the field is uniform in the solenoid. 2 points you have to remember is, so the magnetic field, one part behaves like south pole and another part behaves like a north pole in solenoid, and it is uniform in the solenoid. A strong magnetic field produced inside a solenoid can be used to magnetize a piece of magnetic material like soft iron. When placed inside the coil, the magnetic so formed is called electromagnet. I told you already what you mean by electromagnet. If you take any iron conductor, any good conductor, it may be iron, copper, whatever it is, a metal, and around that you stop wrapping the coil there. Coil ಸುತ್ಕೊಂತ ಹೋಗ್ತೀರಿ. Then one end you connect to one cell, another end to another cell. When the electricity is passed through them, then they behaves like a magnet. Then that coil, it behaves like a magnet and starts attracting the iron fillings which are present in it. This is because of the properties of magnetic field when electricity is passed in magnetic field. Force on a current carrying conductor in a magnetic field. What is the force of a current carrying a magnetic field? The displacement of the rod in the above activity suggests that a force is exerted on the current carrying aluminum rod when it is placed in the magnetic field. It also suggests that the direction of force is also reversed when the direction of the current to the conductor is also reversed. Now change the direction field to vertically downwards by interchanging the two poles of the magnet. It once again observe that the direction of the force acting on the current carrying rod gets reversed. It shows that the direction of the force of the conductor depends upon the direction of the current. Underline this one. Depends upon on what factor that it depends, direction of the current and direction of the magnetic field. So he has given the Fleming's, as I told you already. First one is left hand rule and second one is right hand rule. So if you take the left hand rule, he has given the figure there. The thumb, it is a motion, and forefinger, it indicates the field, and the ring finger, what you call the middle finger, it indicates the current. These three are very important here. One thing is, in left hand rule, it indicates what the flow of current and how the magnetic field are placed around it. Here in left hand rule, one indicates the motion, second indicates the field, and third it indicates the flow of current. Three things are very important here. So you may get the question, what is state Fleming's left hand rule or right hand rule? In right hand rule, we already discussed about it. In left hand rule, what happens is, one, it represents the motion, second, field, and third, it is the current. So he has given some problems on these basis. So these problems I will be explaining you afterwards, because for these problems we need some extra knowledge for this. And he has given the electric motor also. We have simple electric motor, how the electric motor works here. See, in the picture we have, just I will explain the picture, you go on seeing the textbook there. You have two magnets, one is have north pole and one is south pole. In between north and south pole magnet, we have one coil that is made up of aluminum and it is connected to the axle. Axle means a wall. And we have the split rings there. When you start arrange it, and when you start the flow of current, it starts rotating. Why it starts rotating? In the sense it has given there. Current in the coil ABCD enters the form of battery through conducting brushes X and flows back to the battery through brush Y. Notice the current in arm AB of the coil flows from A to B. First term A to B, and second term and C to D, and opposite to the direction current flows from arm AB. On applying Fleming's left-hand rule for the direction of flow of current on the current. So it is nothing very simple, that is, so when you pass the current through it, first it slips into first half position and comes into second half position. So this makes the coil starts rotating continuously in electric motor. So if you get any electric motor, just you open it, you will get the magnets there, and in the magnets will have the conductors and the which is wind or winded up with the copper wire. So when you pass it, the electricity, what happens here, it starts behaving like a magnet and starts rotating it. When our first half flow will be our first slipped, what we call it as half direction, and another one it will be in the other form, that is next half direction. Electromagnetic induction is given there. What is electromagnetic induction? Let us see now. Electromagnetic induction in the sense producing electromagnetic induction. Induction means inducing. Inducing means producing. Magnet, electricity. So we have three words here: electricity, magnet, and induction. That indicates that producing electricity through magnet. Getting the point? Inducing electricity through magnet. So I told you already how you induce electricity through magnet. How you will start producing electricity through magnet. Inducing electromagnetic induction is given there here. So I told you also, I gave an example of intensive sticks. Manali yavadana ondu what you call okay. I already told you, take intensive sticks. Intensive sticks ಅಂದರೆ ಮನೆಯಲ್ಲಿ ನೀವು ಊದಿನ ಕಡ್ಡಿ ಯೂಸ್ ಮಾಡ್ತೀರಲ್ಲ, ಮೊದಲೇ ಕ್ಲಾಸಲ್ಲಿ ಹೇಳಿದೆ ನಾನು, ಊದಿನ ಕಡ್ಡಿ ಯೂಸ್ ಮಾಡಿದ್ರಲ್ಲ, ಎರಡರಲ್ಲಿ ಹಾಲ್ಸ್ ಇರ್ತಾವೆ, ಅಂದರೆ ಎರಡು ಬ್ಲಾಕ್ ಇರ್ತಾವೆ. ಮತ್ತು ಅದು ತೊಗೊಂಡು ಟೇಕ್ ದಟ್ ಒನ್, ಅದಕ್ಕೆ ವೈರ್ ಸುತ್ತಕೊಡ್ರಿ, ಕಾಪರ್ ವೈರ್. ಯು ಕನೆಕ್ಟ್ ಬೋತ್ ಎಂಡ್ಸ್ ಟು ದ galvanometer and insert a magnet inside it. When you insert the magnet inside it, there will be a deflection in the galvanometer. See, we are not doing anything here. Just what we are doing here is we are inserting magnet into the hollow space, but there is a deflection in the galvanometer. Galvanometer indicates what? A small current is produced when we insert a magnet inside the galvanometer. That is what it says. I told you already once, two times I told you already, this is happening here. So what is galvanometer? Instrument that can detect the presence of current in the circuit. So in the electricity chapter we studied that is the galvanometer and what the difference between galvanometer and voltmeter also. So how voltmeter is connected, how galvanometer is connected. They are connected in parallel or they are connected in series also. And we have Fleming's right hand rule also. So Fleming's right hand rule, what it says is, so he is showing three fingers like this. One is movement of conductor, second one is magnetic field, third one is current induced in conductor. First one is movement of conductor, how the conductor is moving, nothing but motion, we use the word. Second one is magnetic field, and third one is current flowing in the conductor. Now we have electric generator. I think you know about the electric generator. We have many electric generators in your homes also. The same thing what is happening in the electric motor, but the main difference is here split brushes. We have two split brushes here. So when you come to class regularly, I will show you, because we have the model of these also. So then only you can understand it clearly. So how it works, on what basis it works, how it is connected, how AC is connected to DC, and how voltmeter is different from everything. So this I will show you when you come to the regular classes. I think it may start from next Monday also. So I will show there so that you can understand it very clearly. Okay. So this is based on electric motor also, same thing. So the spritzings are there, everything is there. So when you start rotating, because there we saw A, B and C, D, but here it is fully total A, B, C, D. It will be rotating completely throughout the system here. And domestic electric circuits we have. I told you domestic electric circuits in the home also. Domestic electric circuits in the sense, domestic means home appliances. In the circuit means how in the home the circuits are connected. So I told you how many volts we are using in the home. Generally we are using 240 volts, and I told you what you mean by AC and DC also. So when you are using 240 volts, what is the capacity of your mobile charger? I asked this question also to check it, and also I told you to check how much your refrigerator needs current, how much your TV needs current, how much electricity your grinder, whatever, mixer, whatever you have in the home. But in home you will be getting directly alternate current, that AC current, but we won't use AC current in our home. So I told you to check the charger, because you will be familiar with the charger of your mobile. So when you check the charger of your mobile, you can see clearly there the big box will be there in front of the charger, that will keep in the switch box. So why that box is so much of big? Why they cannot keep a small one which will be of 2 pins? No, directly you can keep 2 pins inside it and you can connect to the charger. But they will not do like that. You will have some box there, a big box will be there, black or white, whatever it is. So why that box is needed? See, when you are getting 240 volts in your home, the mobile doesn't need 240 volts, just it needs how much? Maybe 1 volt or 2 volt. So when you have 240 volts in your home and your mobile is needing only 1 volt or 2 volt, so how it is converted from 240 volts to 1 volt or 2 volts while charging your mobile? This is the first question. And second question I also asked you, when you go to the shop, if you want the bulb, an electric bulb, I told you to ask, how you will ask to give the bulb? Generally you will not ask to give the electric bulb, no? ಮನೆಯಲ್ಲಿ ಹೋಗಿ ಯಾವುದೋ ಅಂಗಡಿಗೆ ಹೋಗಿ ನಾನು ಬಲ್ಬ್ ಕೊಡು ಅಂತ ಕೇಳಲ್ಲ. ಬಲ್ಬ್ ಕೊಡು ಅಂತ ಕೇಳಿದ್ರೆ ಅವನು ಏನಂತ ಕೇಳ್ತಾನೆ, ಎಷ್ಟು ಕೆಪಾಸಿಟಿ ಬೇಕು ಅಂತ ಕೇಳ್ತಾನೆ. ಅವನು ನೀವು ಏನು ಹೇಳ್ತೀರಿ? ವಾಟ್ ವಿಲ್ ಟೆಲ್? How many volts in you do you tell? That's why I told you to check the bulb there. ನೀವು ಬಲ್ಬ್ ತೊಗೊಂಡು ಬಲ್ಬ್ ಮೇಲೆ ಇದ್ದಿದ್ದು ಓದಿದರೆ ಅದರಲ್ಲಿ ಗೊತ್ತಾಗುತ್ತೆ ನಿಮಗೆ ಎಷ್ಟು ಇದೆ, ಎಷ್ಟು ವ್ಯಾಟ್ಸ್ ಇದೆ, ಎಷ್ಟು ವೋಲ್ಟ್ಸ್ ಇದೆ ಅಂತ ಗೊತ್ತಾಗುತ್ತೆ. Same thing nowadays, we are not getting those bulbs which are used in olden days. Now we are getting incandescent bulbs there which are of 10 volts, 12 volts. We will get more light, more support from that also. But today also in some places they are using there, but they will consume more energy in the sense they will consume more electricity also. I told you check it. Once again you check it the same thing, and once again you can take it. And I told you to write the notes also. I already sent the notes of science and maths also. So check the notes, compare it and write starting the notes. One thing I told you I'll show the motors. It is in our school only, because I cannot show here in presence of you. I can show it. It will be very clear and you will understand neatly. And I will show you what is voltmeter and what is galvanometer also. And I will show you what you mean by difference between AC current and DC current. So you are getting AC current in your home but not DC current. What makes the difference between AC current and DC current? I told you already that also. So that will give you a clear picture about that also. So we have everything in our school. So when you come to school, so it will be shown to you. So in the presence of you only, it will be interesting and then you get a good knowledge of that also. Okay. So for the time being, thank you children. Next, in the next class, we'll continue with another chapter. So for the time being, start writing the notes of this chapter and see you in the next class. Thank you.